Hi, Year 9 students. I'm Norman Wildberger, and here we're going to lay out the Australian curriculum for Year 9 in mathematics. This is our first video, and we're going to start by having a review of some basic arithmetic. Now, arithmetic is the foundation for mathematics, and it's really the basis upon which you make further progress in Year 9 in algebra, geometry, statistics. All of those are going to require a facility with basic arithmetic, and I know that this is a place where a lot of students have a little bit of weakness here and there, and that little bit of weakness ends up making it harder for them to understand the material as you go on. Mathematics is a very sequential subject, so it's important to get the basics right, and then it'll be a lot easier for you to make progress and to understand naturally what's going on. Especially when we make the transition that we do in Year 9 from arithmetic with numbers to arithmetic with polynomials, which is often called algebra. That's basically what algebra is. Okay, so we're going to have a few review videos. In this one, I'm going to start off by reviewing integer arithmetic. And then we'll also talk about a review of fraction arithmetic and then arithmetic with decimal numbers. Okay, so today we're going to talk about the integers. And the integers are sometimes called counting numbers, but they include also the negative numbers. So we're talking about the numbers 1, 2, 3, 4, 5, and 6. And so on, which are usually called the natural numbers, and they're what we use to count. But when we go to the integers, we want to also enlarge our view to include 0 and also the negative numbers, -1, -2, -3, -4, and so on. Now these negative numbers historically were very dubious. So 1,000 years ago, people had reservations about negative numbers. What does negative 5 apples mean? And so on. It's a very natural position to have. And a way of thinking about the integers that I want you to adopt is to think of them as being on a number line like this. We call it the integer number line, where we have the integers all laid out, nicely, equally separated, increasing to the right and decreasing to the left. When we think about it geometrically like that, then we see that there's a natural role for the negative numbers. They just correspond to the positions to the left of 0, while the usual numbers are to the right of 0. This integer number line also gives us a very nice way of thinking geometrically about what addition and subtraction are, and also what multiplication and division are. So let's just talk about addition and subtraction first. So if we have a number like 3, there it is there, we can think about that number as being, first of all, a position on the integer line, but we can also think about it as representing the motion of moving to the right by 3, which we can sort of signify by thinking about 3 as being the same as plus 3. Meaning we're going to move to the right by 3. If we think about it that way, then negative 3 has an obvious opposite meaning. It's moving to the left by 3. So plus 3 means increasing by 3, minus 3 means decreasing by 3. Okay, so then the basic arithmetic with these things can be thought of, one way, is in terms of movement on the number line. It's not exactly like adding and subtracting apples and oranges. It's a little bit different. We're just moving on the position of this line. All right, so some examples. 3 plus 4 equals 7. To interpret that on the number line, we would say, all right, well, 3 is the movement to there. We're really always starting at 0. 3 is to add 3, to move 3 to the right. And then when we add 4, we're moving another 4 to the right. So starting here, going 1, 2, 3, 4 to the right, takes us, of course, to 7. It's a geometrical way of thinking about what that equation means. Here's a variant where we have a negative sign, where we have 5 minus 2. That can be thought of as starting with 5, and then subtracting 2 is moving 2 to the left, giving us 3. Now another way of writing this, which is important to realize, is to replace the subtraction with an addition of a negative quantity. Subtracting 2 is exactly the same as adding minus 2. So minus 2 is this number here and represents a movement to the left by 2. So if we start off with 5 and we add minus 2, it's the same as subtracting 2. It takes us from 5 to 3. And notice that I write this in this way with the minus 2 in brackets, because I don't want to have a plus sign and a minus sign directly next to each other. We try to avoid that usage. It's a little bit unclear. Okay? So we use brackets in mathematics to make sure that things are in the right places arithmetically. Here's a combination of 3 things representing 6 minus 2 plus 3 for a total of 7. 3 minus 5 equals minus 2. There's 3. If we subtract 5, it means going 5 to the left. 1, 2, 3, 4, 5. And we end up at minus 2. So notice that the number line allows us to give meaning to something that would, in terms of apples, be hard to understand. What does it mean to take 3 apples and subtract 5 apples and get minus 2 apples? It's not entirely clear what that means. Maybe we could interpret it in terms of owing apples and so on, but it's a little bit questionable. But when we picture the arithmetic as being operating on this number line, then it becomes very simple and clear what we're talking about. We're starting at this position 3, we're moving 5 to the left, and we get minus 2, which is just as legitimate a position as is plus 2 or plus 8 or any of the positive numbers. And we agree that this minus 5 can also be thought of as 3 plus minus 5. So this is just another way of writing this expression, exactly the same in terms of the content. We are also allowed to start with a negative number. Why not? So we can start with minus 2 and say add 7. Well, that would take us to 5. Let's think about that. So minus 2 plus 7, well, we can check first of all. 1, 2, 3, 4, 5, 6, 7. Yes, if we go 7 to the right from minus 2, we end up with 5. Another way of thinking about that is that minus 2 plus 7 is really the same as 7 plus minus 2. Minus 2 plus 7, same as 7 plus minus 2. 7 plus minus 2 would be 5. Alright, so minus 2 plus 7, we're now at 5. If we add one more, then of course we're at 6. And there's nothing preventing us from stringing together more than 2 or 3. So say 5, subtract 2, that would give us 3. Subtract 6. So 3 minus 6, 1, 2, 3, 4, 5, 6, would be minus 3. And then finally adding 3 would be 0. And there's no reason why we can't get 0 as an answer. 0 is just another position on the integer number line. A rather important special position because it's right in the middle, separating the positive numbers and the negative numbers. Okay, so it's very important for Year 9 students to be comfortable with negative numbers. And thinking about addition and subtraction on the number line is a good way of having a geometrical understanding of those things so that you can imagine what you're doing, that there's some physical meaning to equations like this. Okay, so now let's talk about multiplication, for which the number line is also useful. So suppose we have something simple like 3 times 2. What does that mean? Well, for us, let's think about it as meaning 3 groups of 2. All right, so 3 times 2 is a shorthand for 2 plus 2 plus 2. There's 3 groups of 2 and we're adding them together. So in terms of apples, it would be 2 apples plus another 2 apples plus another 2 apples makes a total of 6 apples. But in terms of the number line, we can think of this as being a movement of 2. We're adding 2, and then we're adding another 2, and then we're adding another 2, for a total of 6. So sometimes 3 times 2 is interpreted the other way, as 2 groups of 3. That's also completely legitimate. Let's just agree, I prefer, to think about 3 times 2 as meaning 3 groups of 2. So that's the convention that I'm going to use. All right, now let's think about how this works with the negative numbers involved. Okay, we have to be a little bit more careful when we're doing multiplication with negative numbers included. So what should 4 times minus 1 be? Well, according to the same reasoning, it should be 4 groups of minus 1s, all added together. In other words, minus 1 plus minus 1 plus minus 1 plus minus 1. And notice that I'm going through the trouble of putting all the minus 1s in little brackets because I don't want to have the situation of having a plus sign and a minus sign following each other. Okay, geometrically, what does that mean? Well, we're starting here, and the minus 1 means we're going to go left 1, and then left another 1, and then left one more time, and one more time again. So for a total of going minus 4. So 4 times minus 1 is minus 4. Well, if 4 times minus 1 is minus 4, then we should expect that minus 1 times 4 should also be minus 4. Because after all, multiplication is commutative. Okay? It doesn't matter if you change the order of the two things being multiplied. So what is this telling us? This is telling us that when we multiply 4 by minus 1, we get minus 4. We get the negative of 4. So multiplying by minus 1 changes the sign of the number. Or in terms of direction on the number line, it changes the direction. So instead of talking about 4 to the right, we're talking about 4 to the left. Beautiful symmetry when we think about things on the number line between right and left, between positive and negative. That's an important rule to remember, that minus 1 times 4 is minus 4. What would minus 2 times 4 be? Well, minus 2 times 4 would be twice minus 1 times 4, so it would be minus 8. Okay, so we can do multiplication more than once. So here's an example of multiplying 2 times 3 first, and then multiplying by 5. So when we have a situation like this with 2 operations, the brackets are telling us which ones we should multiply together first. So 2 times 3 first is 2 groups of 3, that's 6. And 6 times 5 is 30. If we change the order of the brackets, then we would have to interpret this as 2 times 15, which of course is also 30, and I hope we all appreciate that changing the brackets in a multiplication story like this doesn't change the answer. We're going to see that law is called the associative law. Okay, here's some more examples of some multiplications with some signs involved. So if we have minus 1 times minus 7, we're still changing the sign of this thing here. So multiplying by minus 1 changes from positive to negative or from negative to positive. So if we have minus 7 over here, then multiplying by minus 1 takes us to 7. 6 times minus 2, that's minus 12. And you can think of that as 6 groups of minus 2. Minus 2 plus minus 2 plus minus 2 plus minus 2, altogether 6 times. So it's the same as 6 times 2, but with a minus sign, because we're going to the left instead of going to the right. So the minus sign here really comes out front. You can take that minus sign out front and then just calculate 6 times 2 and not forget the minus sign. If we have a minus sign in both terms, then we have to be a little bit careful. The 3 times 4 is of course 12. If there was only one minus sign, then the answer would have a minus sign. But if there's 2 minus signs, they sort of tend to cancel themselves out. Because if we multiply a negative number by a minus, it's becoming a positive. That's the same thing that we had over here. Minus 1 times 4 is minus 4. If we multiplied minus 4 by minus 1, we would get positive 4. Minus 3 times minus 4 is positive 12. We don't say positive, we just write 12. Alright, so I hope this is all pretty familiar. Maybe the connection with the geometry of the integer number line is not that familiar to you, but it's going to be a very important idea in Year 9 maths. Start thinking about the number line and measurement and graphing using this number line, both with positive and negative entries. So it's important for us to get used to this framework. Okay, so we've talked about multiplication of small numbers. Now I have to remind you of something that perhaps you struggled with in primary school and thought, oh, now I don't have to worry about the multiplication table anymore. I'm now in Year 9, but it's not the case. Okay, the multiplication table is still one of the most important tools in your toolbox. And it's very important that you memorize the 10 by 10 multiplication table. So here it is in all its glory, telling you how to multiply any two numbers between 1 and 10 with any other number between 1 and 10. So 4 times 7 is 28. 6 times 6 is 36. 7 times 6 is 42. 7 times 7 is 49. 7 times 8 is 56. 7 times 9 is 63. 7 times 10 is 70. And so on. So some things that I hope we know about the multiplication table, let me remind you, is that 1 times anything is just the number itself. Right? So 1 times 5 is 5. 1 times 9 is 9, and so on. And it doesn't matter if you change the order. So 4 times 1 is also 4. 6 times 1 is also 6. When we multiply by 2, we're getting the even numbers. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and so on. When we multiply by 3, we're getting all the multiples of 3. 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12. And every time we go from one to the next one, we're adding 3. So the differences here are all 3. We're going up by 3 all the time. These are all the multiples of 3. And so on. The multiples of 5 are particularly simple because they all end either in 5 and 0. The multiples of 10 are the simplest because you just add a 0 when you multiply by 10, don't you? Multiples of 7 often cause students some problems. So it's important to memorize these things. And a good way of doing that is to stare at the table and to just practice quite a lot in recalling various products. If you are stuck, let's say you can't remember what 6 times 7 is, but you remember what, say, 6 times 6 is. So 6 times 6, 6 times 7, Well, the difference is 6. So if you remember 36, then you could add 6 to get 42. So there are little tricks like that that can help you remember the table. So why is this important? Because in year 9, we're starting to do algebra. We're starting to work with polynomials. And one of the things that you're doing is you're multiplying one polynomial by another. And multiplying the coefficients of various polynomials is just a part of that process. So, knowing what 3 times 7 is immediately is very important. You do not want to have to rely on a calculator to make that computation. It's got to come from your mind. 3 times 7, it's 21. Okay. So please, no calculators. Okay. Teachers are doing students a great disservice when they allow students to use calculators to do the basic arithmetic. If you're a student, take my word for it, all right? Try to avoid relying on calculators for elementary multiplications. Whenever you can, have a piece of paper beside you and make the calculation on the piece of paper if you're not sure. And teachers, please encourage your students to practice arithmetical skills without relying on calculators. Yes, computers are very important, of course, and the modern world is full of technology, but we're not helping our young people move in that direction by giving them calculators to do their basic arithmetic with. Believe me, okay? You're doing them a disservice. Of course, the calculator companies would like you all to be using their calculators, but it's not in the student's best interest. If you're a student, listen carefully, all right? Try to take your calculator to the side, do the arithmetic by hand. You're going to make a lot of progress with your mathematics. There's another multiplication table that I want to summarize here, a much simpler one, okay, which is just the multiplication table involving positive and negative numbers. And we've already seen it. So what this is just reminding us is that if we have a positive number and we're multiplying by another positive number, we're going to get a positive number. But if we're multiplying a positive by a negative, we get a negative. Or if we multiply a negative by a positive, we get a negative. But if we multiply two negative numbers together, we're getting a positive. So for example, 6 times 7 is 42. There it is right there. But if we're multiplying minus 6 times 7, well then we get minus 42. It's like a minus times a plus is a minus. Or 6 times minus 7 is minus 42. But if you have minus 6 times minus 7, there's two negatives multiplying together. The two negatives multiplied together give a plus. So you get positive 42. So those are very important rules to remember with the signs of multiplying with negative numbers as well as positive ones. Okay, so very important that, painful though it might be, that we practice, that we keep this in our minds. And it's probably not a bad practice if you're a student and you're struggling with math. Okay, I recommend to you that you write out this multiplication table. It doesn't take more than 15-20 minutes. Write it out, line by line, in a neat way. I like to divide up by 5s to give it a little bit more structure. And look at it and memorize it. There's one more thing about this that I want to bring to your attention, and that is this diagonal. These are rather special numbers. They're the results of multiplying a number by itself. So 3 times 3 is 9. That's often called the square of 3. All right, so 3 times 3 is sometimes said to be 3 squared. So 3 squared is 9. 2 squared is 4. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. And 10 squared is 100. So these numbers, the squares, are particularly important in mathematics. And it's particularly important that you know what the squares of these numbers from 1 to 10 are immediately. All right, so for our final aspect of the review today, let's remind you about the laws of arithmetic. So by laws, we mean these are general rules that apply in a wide variety of situations. It's important to identify them, and they're even given names so that we can refer to them. Okay? We're talking about the commutative laws, the associative laws, and the distributive laws. And these are laws that apply to addition and multiplication. All right, so the simplest ones are the commutative laws. We've already talked about that. And those are telling us that when we add two numbers, it doesn't matter if we interchange their order. We're getting the same result. So here, A plus B equals B plus A. Notice that there's letters here instead of numbers. And that's telling us that it works for any numbers. So 3 plus 5 is the same as 5 plus 3. 3 plus 6 is the same as 6 plus 3. Obviously, I can't list all of those possibilities because there are too many numbers. But this one rule captures all of them because A and B can be thought of as arbitrary numbers. So whatever number A you choose, whatever number B you choose, if you calculate the left-hand side and you calculate the right-hand side, you're going to get the same thing. And there's a commutative law for multiplication too, which is a little bit less obvious. Okay. This one here is a little bit an interesting law, because 3 times 4 is 3 groups of 4, but 4 times 3 is 4 groups of 3. And I hope you all have some sense of why those two things are the same. Give you a reminder, it has to do with a rectangle. A 3 by 4 rectangle essentially having the same size as a 4 by 3 rectangle. Then we have the associative laws, which are applying to two operations, either two additions or two multiplications, and the question of what order of the two operations we're going to do first. So here we're calculating A plus B first, and then whatever we get for that, we're going to add to C. That's the meaning of this. While on the right-hand side, it's A plus what we get when we add B and C together. The law is telling us that both those are going to end up with the same number. And for the multiplication, it's similar. A times B times C is the same as A times B times C. And that's for any numbers A, B, and C that we're interested in. In this case, today, just integers. So some of these could be negative numbers, and the laws still work. And then there's the distributive laws, which combine addition and multiplication. And these are particularly important in algebra, as we move from arithmetic with numbers to arithmetic with polynomials. It's a big step in year 9 mathematics. So the distributive law plays a big role in that. Very important that we understand this law. Actually, there's two of them, but they're pretty well similar. Let's have a look at this one. So A times B plus C. Here we have a sum of two numbers, and we're multiplying that sum by A. So A copies of B plus C. And the law is telling us that we can think about that in a slightly different way. That it's the same as A times B plus A times C. So the way we usually think about this is we're multiplying B plus C by A. So there's really A copies of B plus C. B plus C plus B plus C plus B plus C, altogether A times. When you think about it that way, you can kind of see that, all right, there's really A copies of B in that sum. There's also A copies of C in that sum. And what we're doing here is sort of taking the A copies of B and putting them together in one expression, and here's the A copies of C. And when we think about it diagrammatically, we're thinking of it like this, that it's A times B plus A times C. We'll often make some kind of motion like this. When we're expanding this thing out, that's what we call this operation, then A times B is the first thing, and then we add A times C. Let's talk a little bit about the brackets here. So I've put this A times B in brackets, and I put this A times C in brackets, just to make sure that we know that we're making that operation first, and then on that operation, and then once we've done the two multiplications, then we add the result. But I should also let you know that these brackets here are a little bit unnecessary. If we didn't have the brackets here, we would still interpret this result in the same way. So the agreement is that if you have some additions and multiplications in the same formula, you do the multiplications first. So there's another way of writing this, an alternate way, which is a little bit shorter and doesn't involve the x's for multiplication. And it's especially used when we're working with letters signifying sort of general numbers rather than particular numbers. So it's very common to rewrite this equation here in this shorter form. So instead of writing A times B plus C, we just put the A here and then just put it beside B plus C. That means A times B plus C. And instead of writing A times B, we just write AB. And instead of writing A times C, we just write AC. So when you're reading this, you have to remember that this AB means the number A times the number B, whatever A and B might be. And this means the number A times the number C. So this here is just a rewrite of this one in sort of shorter form. And there's another distributive law, which is much the same, except that now we have A plus B on the left, and we're multiplying by another number on the right, say C, and we get A times C plus B times C. And we can write that in a similar way, shorter, A plus B times C, just by putting the C beside it, equals AC plus BC, meaning again A times C plus B times C. So we have the commutative laws, the associative laws, the distributive laws. I hope these are familiar to you. Probably not a bad idea to remember the names of the laws. And in any given situation, you should feel confident about applying one of these laws to go from, say, the left-hand side to the right-hand side, or from the right-hand side to the left-hand side. So these laws allow us to manipulate or change the form of something without actually changing the value. Okay, very important. These are sort of foundational things for algebra, which will play a pretty big role in Year 9 maths. All right, well done, people. We've had a good review of some very basic arithmetic with integers. I hope it's solidified your understanding of some fundamental things. And now it's time to practice a little bit. Okay? So mathematics is not just about absorbing things. It's a doing subject. It's an active discipline. It's like doing sports, tossing a football around, swimming some laps. We want to go out and do things to strengthen our understanding. So here are just a few exercises or practice problems that you can try to solidify your understanding of what we've been talking about today, and maybe to challenge you a little bit and give you a few more directions to think about on your own. Okay, so the first question is just to do some basic arithmetic to simplify or evaluate some expressions. So the first one is to evaluate 2 minus 3 times minus 11. So here we have minus 3 plus 4 times 2, and then subtract minus 1 times 5. And 4 minus minus 6 times minus 3. So hopefully, if you keep in mind the geometry of the number line to give you an idea if you're left or right, positive or negative, that will help you in evaluating these things. The second question, we want to verify some of the laws of arithmetic. So here's the distributive law, but it's a special case. Instead of having A, B's, and C's, we actually have real numbers. So 6 times 7 plus 2 is 6 times 7 plus 6 times 2. So according to the distributive law, this should be a correct statement. If you calculate the left-hand side, and then separately you calculate the right-hand side, the two numbers that you get should be the same. So this is a great exercise to, first of all, check your arithmetical skills, and secondly, to give you some confidence and some understanding of what these laws mean. So the exercise is to calculate the left-hand side, namely calculate this, and then calculate the right-hand side and see that they're the same. So what I would suggest that you do to write things down is say left-hand side equals, say 6 times 9, which was 54, and then right-hand side equals 6 times 7 plus 6 times 2, which equals 42 plus 12, and that equals 54 also. So I've just done that first one for you. Okay. Third question, a little bit more open-ended. I want you to have a look at a sum like this where we're adding powers of 2 together. So 1 plus 2 plus 4 plus 8 plus 16 plus 32. Hope you notice that each number is exactly twice the previous one. So this is 2 times 2. This is 2 times 2 times 2, sometimes called 2 cubed. This is 2 times 2 times 2 times 2, sometimes called 2 to the 4th. So each one is a power of 2. And what happens when you add up a string of successive powers of 2 like this? Okay, once you calculate that, you might think, well, what happens if we go further or if we go a little bit less? Is there some kind of rule here or pattern that that's working here? Right? It's a great exercise. And here's another kind of important kind of sum. We're going to add up all the numbers from 1, say, to 8. Okay, that's a certain thing which you can calculate. And the idea is to see if there's some kind of pattern. You know, if we replace the 8 with just up to 5, or we went up to 10, or went up to 20 instead, would there be some way of calculating this without having to actually work it out one by one? That's a kind of a mathematical investigation that, as a Year 9 student, you can make. And the fourth question, also a little bit of calculation, involving these square numbers that we saw appearing down the diagonal of the multiplication table. So there's 1 squared equals 1, 2 squared was 4, 3 squared was 9, 4 squared was 16, and so on, all the way up to 10 squared. And the question is to calculate the differences between the squares. To calculate the difference between these two numbers, and then the difference between these two numbers, and so on, and see what the pattern is. And to make it just a little bit nicer, I've also included 0 squared. Okay, you'll sort of see when you do this, but that sort of makes the sequence a little bit nicer. And it also then leads to this next question: how can you extend this sequence using only addition? So suppose we wanted to know what 11 squared was, and 12 squared, and 13 squared, and 14 squared, and so on. Could we extend the sequence not by squaring 11 or squaring 12, but just seeing what the pattern is and sort of keeping on going? All right, so that's another thing that you can do, give you a little practice with arithmetic, and also a pattern, a number pattern that turns out to be quite important, because the square numbers are quite important in mathematics and in Year 9. All right, so very well, we've done fabulous. We've reviewed some basic stuff with integer arithmetic. Next time we want to go to fraction arithmetic, and we're going to review the arithmetic of fractions. which is probably the most important thing that you've learned in the years 1 to 8. Okay? That's the foundation for algebra. Very important that we understand fractions, and we have a very solid understanding of the arithmetic with them. So I hope you'll join me for that. I'm Norman Wildberger, and we'll see you next time.